Hey guys, welcome to the Section 2 recap video on games. So let's go ahead and talk about what a game is to start off. So I'm sure all of you guys have played games before, but the kind of formal definition that we're going to go with for 188 is that games are, a type of problem where we have some set of agents, which are going to be the players of the game, a set of states, and then a set of actions that each player can take. Then there's going to be a couple of different kinds of games that we're going to look at. So the first one is the adversarial game. So you can think of this as something like chess, where there's two players and they're playing against each other. We also can call these games zero-sum games because for adversarial games, the score of one player is going to be opposite to the score of the other player. So what that's saying is if player A wins, then player B loses. There's kind of no scenario where both of them can win. So the search algorithms that we're going to use to solve these adversarial games are going to be Minimax and Expectimax. And that's going to be the bulk of what we're talking about in this video. Other than adversarial games, there's also non-zero-sum games, which is basically the opposite. You can have multiple agents who are not necessarily trying to beat the other agents. So you can kind of have cooperative behavior, but the algorithms for that aren't quite as interesting. So we're not really going to be focusing on that for this lecture. Okay, so let's start off by talking about the Minimax algorithm. So you want to use the Minimax algorithm in cases where the games are deterministic. So in other words, if you take an action, the action will complete with 100% probability, right? And the goal of Minimax is kind of to calculate the best set of actions given that both players are acting optimally. So typically a Minimax tree will look like this picture that I have below, where you have some maximizer nodes, which are represented as upward pointing triangles, some minimizer nodes, which are represented as downward pointing triangles, and some leaf nodes, which are represented as squares. And the minimizer is going to be trying to minimize the value of these leaves, and the maximizer is going to be trying to maximize the value. Okay? And then the goal of Minimax or any game solving algorithm is going to be to fill in the values of these intermediate nodes and to come up with an optimal policy. Okay, so let's look at what Minimax algorithm is. So here is the pseudocode. So we have kind of a dispatch function value, which is just going to be the value of a state. If the state is a terminal state or a leaf node, we're going to return the state's utility. Otherwise, if the state is a maximizer, or if the next agent is a maximizer, we're going to return the max value of that state. And then if the next agent is a minimizer, we're going to return the min value of the state. So max value basically means you look through every successor of that state, and then you return the max value of all the successors. And min value does something similar, except you're returning the min value. So this might look a little abstract right now, but we're going to cover an example of kind of how these functions are dispatched through the tree coming up here. All right, so here we go. So this is going to be kind of a standard Minimax tree. I've added a layer here just so we can kind of see better how the functions are going to propagate. So we're starting here at the top with our max node. Here, this max node is going to start with its children from left to right, and it's going to call the value function on the children. Now, we know that the next agent is a minimizer, so the value that we're going to be getting is going to be the min value. Okay? So max will start by calling min value on its left child. This left child will then call max value on its leftmost child because the next layer under this min node is a maximizer node. So we'll call max value on this. And then this node, this maximizer node, will get the best value from its children, which are both leaves. So the value for this max node will become 10. All right. Now this min node will go to its next successor, which is going to be this max node here. It'll call max value on that. And then this max node will return 7. Okay. So then min takes the minimum value of both of these and assigns itself 7. So now we're back up to this topmost max node. And then we'll call min value on this top max node's right child. Okay, and then it continues until we filled out all the values of the tree and we can come up with a policy. Alright, hopefully that helped you see the behavior of Minimax. So another thing that we'd like to explore for Minimax is the idea of pruning. So the idea that we don't necessarily need to see all nodes in order to come to a conclusion about what our action should be. Okay, so let's look at this example here. So this is another standard Minimax tree. This max node will start by calling value on this min node. This min node will return 9 because 9 is the min between 10 and 9. And then this max node will call value on this right min node here. And then this right min node will look at its children. Okay, so the first child that it sees has a value of 2. Right now, even without seeing the 16 there, we know that the value that this min node is going to return will always be less than or equal to 2, right? Just show that there. And why is that? That's because we looked down at this left child and we saw 2, and this min node is never going to return a value higher than 2 because otherwise it would just return this leftmost child here. Now, we can kind of see that if the maximizer goes down the left path, we're already guaranteed a value of 9 here, okay? So no matter what any of these other values are, we're guaranteed that we're never going to take this path, which means we don't have to look at all the children of this min node in order to solve our tree, right? So in particular, we don't have to look at this rightmost leaf, which is 16. All right, so that's going to be the basic idea behind alpha-beta pruning. So let's look at how this implementation is going to work. For alpha-beta pruning, we're going to keep track of two values, alpha and beta. We're going to call alpha the best value for the maximizer on the path to the root, and beta is going to be the best value for the minimizer on the path to the root. And then we can kind of supplement our max value and min value functions from before with the alpha-beta code. Okay, so the alpha-beta code goes in this block here. So let's go over what these conditions say. Well, for max value, recall that beta is the best value for a minimizer node on the path to the root. If we're looking at the max value of a node and we find that v, the value for that node, is greater than beta, so we found a value that's higher than the best value that the minimizer can guarantee on the path to the root, we're just going to return v, right? And the intuition there is if v is better than beta, the minimizer is never going to explore down this path. So we can just prune the rest of the children, okay? Otherwise, we're going to update alpha as the best value that the maximizer can see, and then we're going to move on to the next successor, right? Passing in alpha and beta. The minimizer is kind of a symmetric case. If the value that we see for a min node is less than or equal to alpha, which is the best value for max on the path to the root, then we're guaranteed that the maximizer will never come down this branch, and we can again return v and not look at the rest of the successors. Okay, and then here we'll update beta to be the minimum between beta and this new value, so beta remains as the best value for min on the path to the root. Okay, so that's it for Minimax. Let's move on to Expectimax. Alright, so like we said before, Minimax is the algorithm that you want to follow if you're expecting both of your agents to behave optimally. But of course, there's going to be a lot of games where you're against a player that's maybe not so good, or maybe that doesn't act optimally. So if you think about the Pac-Man case, this is the case where you have a ghost that maybe isn't adversarial, maybe it just takes some action with random probability, right? So in a case like that, you don't necessarily want to do Minimax because it might not give you the highest expected reward. Okay, and those are the cases where we want to use Expectimax instead. So Expectimax is for games where the outcomes of actions maybe are uncertain. So instead of taking an action deterministically, you have an agent that just takes an action at random. And rather than calculating the outcome assuming all agents act optimally, we're going to calculate the best expected outcome. So just to show you guys an example, if we have a tree that looks like this, if we were to solve this tree using Minimax, kind of assuming that instead of these chance nodes, we had min nodes instead, the value for this node here would be 1, the value for this node here would be 0, and then so the max node would choose to go left, okay, because it wants to avoid the 0 here. However, if these are chance nodes instead, which choose an outcome with equal probability, so 50% chance of these chance nodes to return the left value, 50% chance to return the right value, then it's kind of the case that we want to risk going right because there's a higher expected reward for this right node, right? Because on expectation, the value for this left node is going to be 1, the value for this right node is going to be 50. So that's the intuition that you want to have when it comes to Expectimax. And the code is pretty simple. So all we want to do to calculate the expected value of a state is take a weighted sum over all values of the state. So what that means is we're going to initialize the value at 0, we're going to loop through all successors, and then we're going to add the probability of getting that successor times the value of that successor to our total cumulative value, which we're going to return at the end. All right. So again, working out this tree using the Expectimax code, first max is going to look at its left child. We're going to take the expected value between the two leaves for this chance node, and we're going to get 1. Then we're going to look down this right child, and we're going to take the expected value for these two leaves, and we're going to get 50. So we'll choose to go right instead of left. Okay, so almost done here. The final topic that I wanted to cover was utilities. So utilities are super simple, and we've already used them a lot. But basically what they are is a function from some state in your problem into real values. And we say that utilities must be rational. I'm not going to spend too much time on this, but basically there's just a list of rational axioms that your utility must satisfy. Okay? Now, utilities are very simple. You just kind of plug in some value into a function to get the utility. But I did want to cover how utilities work for lotteries. So let's look at a basic example. For this lottery here, what this means is we have a probability P of getting outcome X, and then a probability 1 minus P of getting outcome Y. So how do we take the utility of a lottery like this? Well, basically what the utility is going to end up being is a weighted sum of the probability of the outcome times the utility of the outcome. So for this simple example, our utility can be calculated as the probability of getting outcome X, P, times the utility of X, plus the probability of getting outcome Y, which is 1 minus P, times the utility of Y. Okay, so very simple. And then just in general, the equation for the utility of a lottery is as follows. So you have this lottery with n outcomes associated with n probabilities. The utility of this lottery is going to be the sum of I from 1 to n, so the sum over all outcomes of the lottery, the probability of that outcome times the utility of that outcome. Okay, so that just about does it for our recap this week. So I will see you guys next week.